general relativity, step by step. I've been talking about tidal forces caused by a non-uniform gravitational field, and what I'm going to do now is to talk about tidal forces using index notation, tidal forces in the Newtonian case, using index notation, so it'll be clear how we can generalize it to the Einsteinian case, and then we can use that to understand the Riemann-Christoffel curvature tensor. Well, we better start out with the equation of motion of these particles. We've got d2xi by dt squared. Here I'm going to be using notation, indices I, j, k, and possibly l, which go over 0, 1, 2. Oh, not 0. They're just the spatial components. So they range over 1, 2, 3, and that equals minus di phi by di x. What letter did I use? I. Where phi equals the Newtonian gravitational potential energy, measured in joules per kilogram. This is just absolutely standard Newtonian physics. Okay, well that's what I want to do. But what this does is give me the absolute motion of these particles, and they're all piling down into this black hole here. But what I want to do is to see how they look like to me, who is falling with them. So I need to look at relative motions here. So I need to think about a particle at position xi. There it is. Let's call it x, let's say. And here's one at x plus n. And that might be accelerating in a different way. They might be accelerating in a different direction. So I need to work out the relative acceleration, which equals d2xi xi plus ni by dt squared minus d2xi by dt squared. That's equal to the relative acceleration. So I can get a handle on this spaghettification process here that's occurring. Okay, so I better evaluate this thing. What's that? Well, that's d2 by dt squared of xi plus ni which is equal to minus di phi by di xi, but evaluated at point x plus n, because we're looking at it at a different part of space. So we've got the acceleration of this particle here, which is responding to changes of gravitational potential here, and this particle's at a different position in space. And so we've got to evaluate the gradient, we've got to evaluate the differential at x plus n. Well, what's that equal to? Well, that's equal to minus, I'll put the minus outside there, it's di phi by di xi evaluated at x plus a second order term which accounts for the fact that we are evaluating it at a different position. So that's nk di x, k of course summed over k, times di phi by di x, what letter did I use? I, plus higher order terms. But I'm going to assume that this guy n is small, or the components are small. Okay, so what I've got to do now is to subtract one from the other, and I need to work out d2 by dt squared of xi plus ni minus d2 xi by dt squared, using that formula there. And I'll do that in the next screencast. Stop there.